Equilibrium and elasticity is chapter 11. So when we talked about equilibrium with just forces or static equilibrium, this means no translational acceleration and no angular acceleration. So no acceleration at all, meaning when you sum up all your forces and torques, what do they equal? Zero, okay? So your net force and net torque is zero. Now, there's a whole class on this in engineering. It's called statics. They do things slightly differently because they get real into the weeds. We're doing it more on the theoretical side. The only real exciting thing that happens here is you can so right now when we've talked about torque, there's a rotational axis, okay? It's usually pretty obvious when things are moving where the rotational axis is because that's the part of the thing that's staying still, okay? When nothing is moving, you can do this interesting mathematical thing where you can choose any point to be the rotational axis. Now, why might you want to do that? What does that do to the torque? It means you can set certain torques to zero, which means you can eliminate forces, okay? Because what happens when your R is zero in torque? Yeah, and then torque's zero, all right? So the strategy here is always like if there's a force that you don't know or a force that you don't need, you can choose the rotational axis to be at that force, so it goes away. Okay, and also by moving the rotational axis, you can get multiple torque equations and create a system of equations that's easier to solve. So there ends up being a lot of flexibility in how you can do these problems and multiple ways to solve them. Of course, remember you can choose any point to be your rotational axis, but there's some that work better than others to make your life easy unless you want to do a lot of math. So you want to choose a point where lots of forces act, so you can get rid of lots of terms, or a point where you have a force that you don't know and you don't have any way of finding it out, okay? So you use it to get rid of things. Oh, we finally have a clicker question. So here is a clicker question. Try this out. Either A, B, or C. Please discuss. We'll vote again. I feel like we're gonna have to go over this because the answer is not A. It's C. Yeah. So let's practice torque again. Let me just fine. Here's our scale. I have to draw it now. That's why I didn't want to do it. Okay. Oh, I hate drawing. I don't know. This is not the best drawing I've done. All right. Sorry. Oh, man. Not my day today. All right. So here's my terrible rendition of this problem. Also, what kind of scale looks like this? Scale. And then you have, oh no. Okay. Then you have this thing, and that's 1,000 newtons. Okay, what are the forces acting on this thing? And by this thing I mean this plank or whatever this is. Give me some forces.
There's tension. Wouldn't that just be mg?
Yeah, so this will be, well, it's just 1,000 newtons, right? This is 1,000 newtons. All right, anything else?
Gravity?
There's gravity of this thing, but it's a massless rod, so the gravity is zero because 0 times g is still 0. Anything else touching this rod has no mass.
The other side that's keeping it.
Yeah, there's this thing, which we don't even know. We'll call this F question mark, okay? It's not a force that we could easily know. It's like, it's tricky because there's a pin here, and so we don't know what angle the force is at. It's a mystery force. And then you also have a normal force from the scale, right? And which one is going to be what the scale reads? the normal force, right? So we're looking for, oops, what the heck? Okay, we're looking for this thing. Nope, don't do that. We're looking for this thing, okay? So if we're gonna do this as a torque problem, where should we pick our pivot point?
At the scale.
Well, we know this force, and it's probably useful because it's given as a number. We need to know this force. We don't know what the heck this force is. So which force do we want to get rid of?
That one.
The one we don't know what the heck it is. So we're gonna put our pivot point here, which coincidentally is actually where this thing would pivot, but that's not necessarily why that matters. If we call this length, well, if I could draw that better. If we call this thing length L, right? And this is about halfway. This is gonna be L over 2. So if we sum up all of our torques, right, that's going to be L times 1,000 newtons, right?
Mhm.
Plus N, so times, what is it, L over 2. Okay, and what does that equal? Was this thing moving? So what's our net torque? 0. The other thing we wanted to keep in mind is the sign, right? Which one of these has a positive sign, which one has a negative sign?
The negative 1,000.
Yeah, which actually doesn't matter. All we need to know is that they're opposite signs, right? Because it all adds up to 0, so we don't have to worry about acceleration. But essentially what this says is if we're searching for n, we get, we can cancel the l's, right? Because they're in each term. So we end up with 1,000 newtons is equal to n over 2, which means our n should be 2,000 newtons, which n's not the best choice for this force because it matches the units, but you get the idea. So that's how we get our 2,000 newtons. We just sum up our forces, we use our second law for torque, and we set them equal to mass times acceleration. Acceleration is 0. And the tricky thing here is picking the pivot point because we want to get rid of this mystery force. Okay? All right. So that's how we get an answer of 2,000 newtons. So our force is just twice the weight. All right? Okay. Any questions? Cool. So let's talk about balance. For an object to balance, its center of gravity and therefore its center of mass has to reside over its base of support, okay? So that way gravity does not exert a torque, all right? So when you're doing this in terms of, it's a form of equilibrium. So let's talk about base of support, and that's how we get stability. So for instance, if this is I think they chose this because this is when the Ford Explorers were rolling over a lot. It's a design flaw. But yeah, so the base of support is basically the points of contact, right? The distance between the points of contact. So here we have our wheels touching, which means our base support has a wide width, okay? Once the car starts to tip, the base of support changes, okay? So now there's a torque because gravity will bring the car back down as long as the center of gravity is over the base of support, okay? Once you reach this point, now you have this critical angle at which point the vehicle is exactly over the base of support because now your base of support is just this point, so it balances. But once you get past that, what happens? You fall over, right? You're not gonna go back to your equilibrium position. So the critical angle is the angle at which the object will balance when its center of gravity is directly over the pivot point. And if you do any sort of, as a person that can change your shape slightly, this is an important thing. So when you're trying to balance, you have to shift your weight over something. So if you want to, here, stand up, guys. Okay. So pick what's a good base of support where it's hard to knock you over? What's a good stance? Pick your best stance for not being knocked over. You wanna have like a shoulder width distance, like a wider stance is a little bit better. Too wide and it's just weird, but like so now I want you to stand on one foot and notice what you do with your weight, okay? What did you do with your weight? You moved it over towards the foot. Why? Where's your center of mass now? Yeah, it should be right above the base of support, okay? So intuitively you know to do that, but that's what we need to do in physics to balance. Okay, you can sit down. So that's balancing, and that's why if you're going to be, if somebody's gonna try to knock you over, you don't wanna be standing like this, you wanna be standing like this. It's also good to like lower your base of support, but that's a slightly different thing. Why would you wanna get lower? Yeah, because, well, what do we know about torque?
The further the distance.
Right, because where's your pivot point if someone's jumping at you?
Feet.
Your feet, right? So if you move your R, you make your R smaller so it's closer to your feet, then you're harder to knock over, which is nice. Okay, so we're gonna try an example with a cat. So we have a 2 meter long board weighing 50 newtons. It extends out over the edge of a table. 40% of the board's length is off the table. And we wanna know how far off the edge a 25 Newton cat can walk before the board begins to tilt. So this is something like this. If we have something, I can actually do exactly 40%. So we put this thing, this is like a plank, and you have, which one should be the cat? This York peppermint cat patty will represent the cat. So obviously if the cat's anywhere over here, does this thing tip over?
No.
No, okay. But the cat can go over here and it doesn't tip. This might not be a very good cat. We might need a heavier cat. We use, it's probably a bad idea. We use my phone. Okay, so I'm just gonna hold this here. Yeah, it's pretty quick. But over here, not tipping, but there's some point at which this is going to start to tip. Okay? Now, where is the force acting on this thing when it starts to tip? Yeah, the pivot point is right here, but that means there's a normal force, right? And what do we know about this normal force? What's the angle of this normal force?
Perpendicular to the surface.
It's perpendicular to the surface when you're here, but once it starts to tip, you're changing your angle. So this is kind of a little bit of a mystery force. But the critical point is at the point at which the normal force over here changes, right? It goes to 0, okay? So we're gonna set this up, and we're gonna start by drawing the forces.
I was always
Doesn't wanna do it. Now you have to watch me draw a cat.
a lot.
I apologize. Paste. Ugh. Stupid Steve Jobs. Okay. So we have a 2 meter long board weighing 50 newtons and extends out over the edge of a table. 40% is off the table, and I demonstrated this with this meter stick, so we have a general idea of what's going on. So we want to know how far the cat can walk before the board begins to tilt. And so where's the center of mass or the center of gravity, if you want to call it that? Where's the center of mass of the plank? On the table, right? It's a 2 meter plank, so it should be at about 1 meter because it's a uniform density object that's 2 meters long, okay? What about the cat? Are we gonna treat the cat as like a 3-dimensional object or a point in this case?
Point.
Treat it as a point. So at the cat's center of mass, it'll act as a point, okay? So what we're really looking for is the combined center of mass of these two objects. But we're gonna do this by using equilibrium. Our equilibrium process is to sum up all of the what? What are we summing up? Torque or force, but in this case torque. And what does it equal?
0.
0, okay? So we don't have to worry about acceleration constraints because really all the signs and coordinate system things with acceleration constraints came from the fact that, sorry about the beeping, came from the fact that we needed to make sure we didn't get our signs wrong, but 0 doesn't have a sign, so you don't have to be nearly as careful about signs for this. You just have to know there's positive and negative torques. It doesn't matter if you label them correctly, positive or negative, as long as they're opposite, right? So if you pick this direction to be positive, then that direction is negative. So that should be a little bit intuitive, but you don't have to be quite as careful as you were before. That doesn't mean just ignore signs. It just means that you don't have to like be as thoughtful about your coordinate system. Okay, so I'm gonna draw this, unfortunately. So here's our table. Nope. Why does this thing not like, oh, there we go. And then we have a plank. No. I wish that this thing believed me. Let me try this. Oh my god. We had this problem last time too. That's close. Okay. Here's the plank. This is a wooden plank apparently. No. Okay. Yay, okay. I didn't even remember the color. So here's this guy. We have to, oops. So it's 40%, so that's like there-ish. Okay, so start with the center of mass of the plank, okay? So that's gonna be right in the middle. We're gonna put the cat over here. This is not a good picture of a cat. Okay, there's your cat. And now we wanna do some coordinates, okay? So, well, first let's do some forces. What are the forces we're dealing with? These are relatively easy.
Normal?
Yeah, the normal force, where's the normal force gonna act?
The center.
There should be a normal force kind of all over here, so we're gonna kind of not quite think about it because what are we gonna,
Board is its weight, right?
well, right when it tips, where's the normal force gonna be?
To the right.
The pivot point is here, right?
Yeah.
So when the board starts to tip, so like if we have this guy, oh, it is following me. When the board starts to tip, the only normal point of contact is gonna be right at the pivot point, okay?
But isn't that what's tipping, so wouldn't the weight be on the right? Or it would be the cat's
So
weight, right?
cat, right? Center of mass of the board, center of mass of the cat. So we have weight from this, and then the only other force is gonna be the normal force. And at the critical point, right when it starts to tip, the normal force acts here. Now what's the problem with that normal force?
Is it also being pushed up by the the ledge?
Right at the time that it's happening, we don't exactly know which way it's pointing, right? Because it's right on a ledge. So like when you're looking at the normal force here, you know it's pointing up because this is our surface. But at this point, the normal force can point like this way or this way. It's like the hinge
It's like
normal
that car
force.
thing you showed, right?
Yeah. So so we have a pivot point. We'll put that here. Make that a star. And so we have three forces. We have weight of the cat, we have weight of the board, and then we also have some mystery normal force over here, okay? Now remember, when we're talking about torque statics, it's important to choose the pivot point carefully, and in this case, we're gonna pick it where the normal force is, because the normal force is kind of annoying and we don't need it for anything anyway. So we're just going to put the pivot point where the normal force is, because then what happens to the torque from the normal force? Goes away, okay? So, yeah, let's say we have mg for the cat and big mg for the board. So then we just need some distances, okay? And we need the distances because it's torque. Okay, so we measure our distances from the pivot point. So the distance to the cat, well, let's start with the easy distances, right? So this whole thing is 2 meters, which we'll call L. Okay, where is the center of mass? 1 meter. Where is it with respect to the pivot point? So what's this distance?
0.2 meters.
0.2.
Yeah, that should be 0.2, right? Because this is 40%, this is 60%, and so this is going to be 0.2. So 10% of 2 meters. So 0.2 meters. We're gonna call the distance to the cat. Do we know what the distance to the cat is?
No.
That's what we're trying to find. So we'll call that x, which means we don't know and we're gonna solve for that, okay? Anything else we need to get this going? I think that's good. Okay. So now we go to our torque equilibrium problem. I'm gonna say 0 is equal to the sum of the torque, just because this will look prettier when we start writing. So this will be torque of the board plus torque of the cat. Remember, these are vectors. But that just reminds us that we have to care about sign. So the torque of the board, so first off, what are the angles between our R's and F's, our distances and forces?
90.
90, because remember, torque is R cross F, which is the same as saying RF, RF sine theta, but sine of 90 is always 1. Okay, so we can ignore the sine of theta, but that's because it's 90. It's not because it doesn't exist, okay? And so the torque for the board, that's going to be the distance, that's 0.2 meters, times the force, which is going to be 50 newtons, because we're saying that's the board. I guess we don't need mg, we can just call this 50. Hang on. And then this one is 25. So that's a little bit easier. And then this other one, is it plus or minus? The other torque, the cat torque.
Minus.
Yeah, minus. And we can go with the clockwise, counterclockwise, but it really just has to be opposite from the torque for the board. So we'll say minus x times 25 newtons, which is the weight of the cat,
The
okay?
reason why it has to be minus is because it's on the other side of the pivot point. Like
The
you
reason
added
it- yeah,
you've added
so the
everything
reason
on one side
it's-
of the pivot point to the other side of the pivot point.
So like, what, you remember for torque, it depends on which way it would cause it to rotate. So this weight causes it to rotate in this direction, this cat causes it to rotate in this direction. So in the case of setting up a coordinate system, this would be negative just because it's in the clockwise direction, and this would be positive because it's in the counterclockwise direction. In the case of an equilibrium problem, it really just has to be opposite. If we know that one rotates it one way and one rotates it the other way, we just have to define that they're different signs. Okay, so we're gonna solve for x, and x is gonna be equal to 0.2 meters times 50 newtons divided by 25 newtons, and that's going to give us a value of 0.4 meters. So if we were gonna draw this on here, that means it's 0.4 meters past this, okay? So it's 0.4 meters past the pivot point. All right? So the cat can walk out to 0.4 meters past the pivot point. Anything beyond that and you tip.
So it can walk out the whole way.
No.
Right? Well, if it's hanging out 40%, and it can go 0.4 meters past.
40% of 2 meters isn't
2 meters. My bad.
is not quite.
Yeah. 1 meter.
So it hangs 80 centimeters over. It could go about halfway off the edge. Yeah. Okay. Any questions about this? The equilibrium's a little bit more straightforward. This is a nice example. The next one is slightly less nice. I'm gonna have you guys start that one, and then we'll go over it together. So we have a 10 kilogram, 2 meter long plank, just the same plank apparently, different mass, and it rests against a wall so that one end is held up by a rope. So you can see this is just sitting on the wall right here, and here's your rope, okay? and the rope's connected to the other end, and we wanna know the tension in the rope and then the minimum coefficient of static friction here, so that it doesn't fall. Okay, so nothing's moving, so there's no acceleration, but we have to set up all of our forces and torques to solve for these two things, all right? So I'll give you guys about 5 minutes and I'll come around and we can work on this together. So we want to start by, like pretty much all of these problems, we start by drawing our forces. So what forces are we dealing with here?
Oh no, tension?
Definitely tension.
Normal force.
Okay, where's the normal force?
Off the wall.
Off the wall. All right, we have at the center of mass, we have the mg, right, the weight. And then there's one more,
Friction.
friction, which points up, and it's static friction because we don't want this thing to slide because equilibrium, okay? So that's all of our forces. We know this plank is 2 meters, so the distance to here is 1 meter, the distance to here is 2 meters. So we wanna sum up our forces and torques. And what two things are we asking for? What problems are we looking for? We have the tension in the rope, and then we have this coefficient of static friction. So let's start by going with the tension in the rope. So we have all these forces. These problems usually are best to start with torque, although you can sum up the forces too. So we'll start by saying we know that the sum of the torques is 0. So to calculate the torques, our net torque is going to be, first we have to pick a pivot point. And where's a good place to pick a pivot point? So remember, it doesn't actually matter where it's rotating because it's not moving. So what would we want to, there's a couple of good strategies. One that makes the math easy, and that includes getting rid of forces that you don't know, because we're trying to solve for tension, so probably putting the pivot point here, putting the pivot point here would be counterproductive because we get rid of tension, which would make it very hard to solve for tension, okay? We don't want to put it here because we already know what mg and the distance are, so calculating torque is easy. But we do have two forces we don't know here, okay? So we're going to eliminate them. And when we do these sorts of equilibrium torque equations, you can have multiple equations for torque. You can move your pivot point and solve for a new thing, okay? So you can, it's just a tool to get to the variables that you need. So since we're calling this our pivot point, that means this distance is 1 meter, and then this distance is 2 meters, okay? And we have two torques. So the first one is just going to be mg, and that's times the distance, which is 1 meter. I'll call that L over 2. We'll call this L, all right? And then that's going to be minus, if you want to be real nitpicky about signs, you can call this minus because it would be the one going in the clockwise direction. But because it's all equal to 0, it doesn't totally matter. And then we have, and what's the angle between L over 2 and mg?
Sine 30?
No, the angle between this, and this.
90.
90. So that's sine of 90, no problem, okay? That goes to 1. Over here, we end up with tension times L, right? That's the distance, and that's sine of 30 degrees, okay? So this time we didn't get to drop the sine. The other way you can do this is you can break tension into x and y, so this would be t sine 30 and t cosine 30. We'll have to do that later anyway, but you just use the perpendicular force component and it gives you the same thing, okay? So we know all this is equal to 0. So we want to solve for just tension. We can get rid of the L, which is why I called it L, because you can just cancel it out because it's in every term. So we solve this and we end up with tension is equal to mg over 2 sine 30. When you plug all your values in, that's going to be 10 kilograms, 9.8 meters per second squared, and then 2 sine of 30 degrees. That's going to give us 98 newtons. So our tension is 98 newtons. Okay. So that part's relatively straightforward. You draw out all the forces and then you solve a torque equilibrium equation. The real tricky part is picking the pivot point to make your math life easier, okay? But we still have to find something else. What is it?
The minimum coefficient?
Yeah, the coefficient of friction, right? So I'm gonna move this over. There's actually multiple ways to do this. Anybody have any ideas about where to start? So like I said before, you can write out another torque equation, right? But remember, we have two unknowns because we don't know coefficient of friction and that's also made up of normal force. We don't know normal force. So we need at least 1 to 2 more equations because 2 unknowns means at least 2 more equations. So remember, when we're talking about equilibrium, we can also use force. So we can either rewrite a bunch of torque equations, which is annoying because torque's more annoying than force, or we can just add up the forces in the x and y direction, which is something we should probably be pretty good at this point. So let's sum up our forces in the x and y direction. It's a good review too. So what are the forces in the x direction?
The wall.
Yeah, n, right? So we have n minus t cosine 30, and what's that equal to? What do all of the net forces and torques equal? 0. So that equals 0. And then we sum up all the forces in the y direction, and that's going to be t sine 30 plus mu s n. That's what this is, mu s n, plus mg. Oh, sorry, minus mg. And what does that equal?
0.
0. Okay. And since we know t, right, now we have 2 equations and 2 unknowns, and now it's just algebra, all right, because we can plug in our tension that we found from before. We'll start by finding normal force, so we'll start with this equation, and we'll say normal force is equal to t cosine 30 degrees, which is 98 newtons cosine of 30, which gives us 84.9 newtons, so that's the normal force. Then we plug in to find our coefficient of friction, so we use this equation. We end up with t sine 30, so mu s n is equal to mg minus t sine 30. So mu s is equal to mg minus t sine 30 divided by normal force. We plug our stuff in, so that gives us 10 times 9.8, that's mass times g, minus 98 sine of 30 degrees divided by 84.9 newtons gives us 0.577 as our coefficient of static friction. Okay, so as we often end up doing in these cases, we end up with equations. So we end up with 3 equations and 3 unknowns. All we're doing is summing up all the forces and torques and setting them all equal to 0. Okay, that's how we get our equations this time. So drawing your forces and choosing your pivot points are the only really tricky part, because remember, now we can't just draw forces as up, down, left, right. They have to be where they are and like where they're acting on the object to get torque. Okay, because we also need R. Any questions? No? Feel Feeling good? Tired? Yeah. There's a whole class on this. It's called statics. Yeah. All right. It's a very sad histogram. Where is it? Oh, there it is.
Oh,
Yeah, I got B.
Hey, B. Everybody believes it's B. You guys are getting good at torque. All right. Oh. Okay. We could go back and see what people actually said, but does people not pick B? Do we need to explain this? You guys, so just distance times force. That's all we really need to worry about. The answer is going to be B. The hardest one to hold is C, right? Because it's a lot of mass far away from the pivot point, followed closely by D, right?
Mhm.
Which should be, and then A and B are equal. A and B, all right? Yeah, okay, cool. We have another problem to do. Give you guys about 5 minutes, and then we'll go over it together. So, we have, I'm gonna try to draw a beam again. So we have scales at either end of the beam. Hey, I did it. Okay, exciting. So here are, we'll call this a scale. Alice is 3 meters from the left scale. We wanna know what each scale reads. Okay, so here's, how long is this thing? 10 meters long. So Alice is here. Okay, what are our forces?
Force of Alice.
Force of Alice. We'll call that mass Alice times G. Any other forces?
There's MG at the center of the board.
Right, mg. We'll call this mbg. Couple more.
Normal force of the scales.
Yeah, normal force. Call this normal force 1
Alice.
and normal force 2. Okay, so we have, and then let's draw some distances. Those are tricky. We gotta pick our pivot point first, okay? So these are gonna both be torque problems. What are we trying to solve?
Scales.
One's a normal force.
Yeah, what do the scales read? So we want, how many normal forces though?
2.
2. So we have 2 things we can do, right? We can either use 2 torque equations, right, by picking 2 different pivot points, or we can use torque and force, all right? And the force will be really nice because we only have forces in the y direction. So probably use force just because it'll be a lot quicker. But you can also solve this, and I'm not going to do it this way because we're running out of time. You can also solve it with 2 torque equations by picking 2 different pivot points. So you would basically pick a pivot point on because you don't know either normal force, you'd pick one here, and then later you'd pick one here and redo the whole equation. That's gonna be way more annoying to do than just using the force. So we're gonna pick our pivot point here, and then we're gonna measure our distances from there. So our first distance is gonna be the distance to Alice, which is 3 meters, and then we have the distance to the center of mass, which is 5 meters. And then last but not least, we have the distance of the whole thing, which is 10 meters. And I wish I had drawn these smaller. I'm gonna move them up. Okay, so there we go. Okay, and then so we start by using our torque equation. So we know that all of our torques have to sum to 0. So that's going to be let's see, we don't have to do this symbolically. So 3 meters times MAG plus 5 meters times MBG minus normal force times 10 meters, Okay, so this is equal to 0. We solve this for the normal force. This is normal force 2. And that's going to be, let's see, 3 times the mass of Alice, which is 50 kilograms, times 9.8, plus 5 times 5 kilograms, times 9.8, divided by 10 meters, should give us a normal force of 172.
Is it better to take away the normal force or to have the normal force and take away the other two? Take away 3 and then take away the 3 mg.
Oh, you mean from an algebra perspective?
Yes.
Oh, I
You
just,
still get the same result, so.
yeah, I should give you either one is fine,
Okay.
yeah. Yeah, so then you have normal force 1, then we're just gonna sum up the forces in the y direction. So that's going to be N1 plus N2 minus MAG minus MBG is equal to 0. Okay, then you just solve for normal force 1. So that's going to be MA plus MBG minus N2. Sorry, I'm out of space here. So that's going to be 55 kilograms times 9.8 meters per second squared, minus 172 newtons. And that should give us, oh, should it be plus? Did I do that wrong?
$367.
No, that's fine. It does give us, yeah, 367. Okay, 360. Something around 367 or 368. Yeah. And which scale were we expecting to read now that we should have predicted this before, but obviously the one that Alice is closest to is going to read a larger mass, right, or a larger normal force, and that's what we got. So that at least makes sense physically. And we're done with equilibrium.